Hello, everybody. Happy Wednesday, February 8th. For today's San Francisco Bay Area PostgreSQL users group, we are pleased to have Christoph Pettis presenting Xtreme PostgreSQL. Before we get started, just a few organizational things. The session is being recorded and will be posted on our YouTube channel. If you don't want to be recorded, please leave your mic. Well, your mic should be off anyway and muted. When we get to the Q&A at the end of the presentation, if you want to ask a question, unmute yourself, ask your question. Your voice will be recorded. If you would prefer not to be recorded, you can send your question to the organizers in chat and we'll relay it to the speaker. If you do not ask a question, you will not be part of the recording. If you're using the most recent version of the app, which we recommend, you can use the raise hand function to join the Q&A queue. If you have an older version of the app which doesn't have this function, please ping the moderators and or the organizers, and we will let you know that you're next in the queue so you can be ready to unmute your microphone and ask your question. Again, if you don't want to be part of the recording, you can convey your question to the organizers. We'll forward it on to the speaker. If you have any technical issues, please message the organizers for assistance. And somebody's not muted. If you drop out of the meetup and are unable to rejoin, post a message to the event page on the meetup, which we'll be monitoring during the presentation. The San Francisco Bay Area PostgreSQL Users Group has two sponsors. We are affiliated with the United States PostgreSQL Association, known as PGUS, a nonprofit 501c3 dedicated to promotion of education and adoption of PostgreSQL. As a disclaimer, I'm the president of the PGUS, but these two things are actually unrelated. Our other sponsor is PGX Inc., the PostgreSQL experts. PGX provides staff to organize the meetup, the recording facilities, the editing, and the YouTube channel. Again, disclaimer, I work at PGX. Again, coincidental. So for today, as I said, we have Christoph Pettis doing Xtreme PostgreSQL. Christoph, I'm going to make you the presenter now, and the floor is yours.
Okay, great. Here's hoping this works. So thanks everybody. Hi, I'm Christoph Pettis. I'm the CEO of PGX. We are a small PostgreSQL focused consultancy based in Alameda, California. I'd also like to apologize because the building decided to take today to work on the roof immediately above my office. So if you hear banging, that's what's going on. So today we're going to talk about how extreme can you get with PostgreSQL. I'm sorry, did I hear a comment? No, okay, great. PostgreSQL has almost no hard limits on anything, and the hard limits it has are kind of absurd. Like you can have over 4 billion databases inside of a single instance, and you can have 1.4 billion relations, tables and indexes inside a single database, and each individual relation can be up to 32 terabytes. And if that's not enough for you, you can recompile Postgres with a larger block size above the default of 8K and get it pretty much as big as you want. Although I'm curious how it would perform with like a 16 megabyte block size. That would be exciting. So, but how fast can you get? Well, there's a GitLab paper which I should have linked to here. It's apologies. I'll add that to when the recording goes up. And they were able to get 360,000 transactions per second, mostly inserts on a single PostgreSQL instance, and not a particularly heavily tuned one either. And we've routinely seen individual servers that are doing over 500,000 inserts per second. So pretty fast. But okay, well, that's all great. But how about we want a really big schema? We want lots and lots and lots of tables. So what can you do for us there? A few years ago, there was kind of a new trend, which was schema-based multi-tenancy, where you would have each customer would get its own schema inside a single database instance. And because of the multiplication factor there, you would get really big schemas. So 250,000 tables per database, not uncommon. We see that all the time. But how? So can you just do this on stock PostgreSQL without editing PostgreSQL.com for doing anything else? Generally, no. You do have to tweak PostgreSQL and make some modifications if you want to get the absolute edges. You want to go to the absolute edge of performance. And we're going to talk about some of these things here. So we're going to talk about these three separate categories. Very large databases, presumably with a lot of read activity. So lots and lots of data, and you're doing queries across a chunk of it. Databases with very high write rates and databases with very large schemas. I am continuing the Postgres ambiguity of using database to mean both an instance and an individual database inside the instance. I apologize. After 25 years of PostgreSQL, it's a hard habit to break. So first, let's talk about big data. So how big is big? A terabyte here, a terabyte there, and soon you're talking about real data. Sort of our view is when a new client comes to us and they say, well, we're 78 gigabytes. It's like, that's not big at all. You could PG dump that if you really had to. Up to about 4 terabytes, I would call medium size, and up to about 20 bytes is largish. And above 20 bytes, it's like, okay, now we'll call it big. And if you're over a petabyte, it's like, ooh, this is exciting. That's a real database. So when you're dealing with database like this, you can't be too rich and you can't have too much RAM, which work against each other because you've given enough RAM, you're not going to be rich anymore. Because databases of this size just aren't going to fit into memory unless, I have seen actually systems with with double-digit terabytes of memory as database servers. And if you could afford that, great, but most people can't. You can go up to 4 terabytes on an RDS instance, though, so that's the costs you a lot, but you can do it. But get as much RAM as you can afford. When you are spending money on your infrastructure, RAM is what you want for these big data solutions. Cores are nice, but max out your RAM before you spend more money on cores. Of course, if you're on AWS, they go up together, so you don't really have much choice. But focus your cost model on RAM. And partition early and often. Partition tables are really your friend here. When you partition, just for anyone who's new to this, you break a single table up into a root table and multiple child tables based on a partition key. In PostgreSQL, you can partition either on a range of values, for example, a time range, from January, February, March. Or you can partition on a hash, which by hash they mean a modulus right now. So you can say, well, we're going to have 20 partitions based on the modulus of an integer key, for example. This is very, very useful. Now, the problem sometimes is partitioning isn't great for everything, because if there's no clean partition key, for example, that you're always going to use in queries, you may end up with a situation where even after you partitioned, you're querying all the partitions, and that's a pretty bad situation. That's worse than just having one giant table. But for things like time series data or data where it expires out after a while, or there's active and inactive data, partitioning can be a huge help. In versions of Postgres like 13 and earlier, if you had a large number of partitions per child partitions per root table, once in the high hundreds to 1,000, there were some serious performance issues. That's gone up a little bit, so it's okay to have that many partitions. 25,000, you're going to start running into issues again. So pick your partitioning scheme judiciously to get that number of tables. Also, when you start doing this, you're going to be pushed into big schema territory also, because you're going to have all these tables. Because child table's a table like any other, it lives in the system catalogs. So stay tuned for that part of the presentation. This data like this really benefits from parallel operations. So Postgres can parallelize a lot of things now: sequential scans, index scans, other things. Be sure to give the system enough workers, because by default, the worker count is very conservative in Postgres. Generally, we say as a good starting point, you can set the max worker processes. This is a parameter inside of PostgreSQL.conf to 4 times the number of cores. And I'm using cores in kind of the generic sense. This is execution units. So whatever your particular CPU architecture calls an execution unit. The parallel workers draw from the pool of worker processes, so there's no point in setting it any higher than worker processes. You want a few background worker processes for other things potentially, like if you're using logical replication, stuff like that. So you want to set the number of parallel workers. We usually say core times 3. And max parallel workers per gather is how many, the maximum number of processes that PostgreSQL will use inside a particular planner operation. So if it's doing a sequential scan, how many individual parallel sequential operations will it do? And we usually say set that to cores. Somebody's unmuted. And one of the things, this is one of the reasons you want to pick your partition key very judiciously, because you want to pick the partition key so you use it in just about every query, essentially every query. And when it's used, it selects just one, maybe two partitions, because right now it doesn't parallelize scans across multiple partitions. It will query each partition in turn and then append the results. And that's can be 1,000 partitions. Even if most of the time it's getting no results out of a partition, you're still paying for that operation. One thing that could be very, very helpful and is not used as much as I would think I would like is partial indexes, which are indexes with a Boolean predicate on it that says essentially only index rows that pass this Boolean predicate that return true. And then if you use that same Boolean predicate in the query, PostgreSQL will favor using that index because it's kind of pre-calculated for it. If the predicate is going to reduce the index size by 50% or more, and this is a very common query, by all means take advantage of this and create them. Once you've done this, do look at pgstat user indexes to make sure that's actually being used, because you don't want indexes just sitting around that aren't being used. They're fairly expensive to maintain. This is also great data for Brin indexes. Brin indexes are a semi-new index type in Postgres that works very well for data where the data on disk ordering matches the ordering of a key. So, for example, time series data is a great example. Time series data you generally append to the end of the table, so it's generally clustered that way, and the key is increasing. And Brin uses uses ranges rather than identifying each individual record. And for summary queries across large data sets, Brin indexes can be much, much smaller than like several orders of magnitude smaller than a B-tree index, and thus faster because it's not having to walk that individual index. On data that's more or less randomly distributed, though, the key doesn't really have any particular mapping to insert order, or the data is being updated a lot, which causes rows to move around inside the table. Brin indexes are not as effective. So, auto vacuum, everybody's favorite feature of Postgres. If you have big tables, they're big, so they're going to take a long time to scan. And each auto vacuum worker can only only grinds through one table at a time. So one thing you can do is reduce auto vacuum cost delay, which, without going into horrible details, is a delay period each time each auto vacuum worker thinks it's done enough for that particular table. It's intended as a way of gating the amount of resources that auto vacuum takes. On a modern system, it's probably okay to reduce it fairly substantially. It's pretty small already now by default, so that the auto vacuum workers finish faster. On a database like this, be generous with shared buffers. The traditional number is 25% of available memory, or sometimes people say 25% of system memory. It's okay to go up to 40% here. There is a diminishing returns point on shared buffers because of the way they're managed inside of Postgres. Postgres will still use the rest of the memory as the file system cache, so you're not wasting it. But assuming you don't need the extra memory for work mem, since shared buffers is permanently allocated to shared buffers, so you can't use it for like big sorts, stuff like that. Going up to 40% is fine. Some systems can go even higher. It's not going to kill you. But 40% on a modern system is probably about the point of diminishing returns. So this isn't directly related to big data, but big data generally means big queries. It's often a data warehouse. It's often a very normalized schema, or like a star schema, and you're joining a lot of tables. So one thing to be aware of is if you're joining more tables than the setting join collapse limit, Postgres switches to it will not try and reorder those, and you can get pretty bad plans there also. Something I didn't mention here is also look at the genetic optimizer threshold. Above a certain number of joins, Postgres will start using the genetic optimizer instead of its regular planner for planning queries. And the genetic optimizer is almost guaranteed to give you a bad plan. So bump that number up if you're joining a lot of tables, like 12, 15 tables at once. So Postgres planner generally tries to figure out, should I do a sequential scan? Should I do an index scan? What should I do optimally for this table? It's pretty good at that. In extrema, though, it can sometimes get confused and favor sequential scans on very large tables where they really shouldn't be. One thing you can do is there's some suggested settings here that will very strongly push PostgreSQL away from sequential scans and focus on index scans. Try these. They aren't perfect for every single workload or configuration, but even if the database doesn't entirely fit in memory, this will generally push it towards doing index scans, and indexes will be primarily cached in memory, and you'll generally get better results that way. Now, if you really are doing operations that touch 50% plus of a large table, these are going to hurt more than they're going to help, so don't do that. But those operations are going to be terrifically slow no matter what on very large tables. One thing that I feel like I need an intervention with people about effective cache size. Effective cache size is a planner hint. It tells the planner roughly that it has this much memory for cache, which is shared buffers plus the file system cache. People really get nervous about setting it very high because I think they think that memory is going to be allocated. And even after explain to them that no, it's never going to try and grab effective cache size worth of memory in a single go, they still feel like it's wrong. It's naughty to set it very high. Sometimes when I'm testing a system, I will go in on a very small system and say effective cache size equals 8 terabytes. Honestly, you can do that. And this tends to favor indexes the higher it goes. And no one's they're not going to arrest you for setting effective cache size bigger than system memory. So experiment with that also to see if the plans are improved. So you've got this giant 8 petabyte database and you need to back it up. Oh, yuck. How do you do this? Most point-in-time recovery backup systems at some point have to do a copy. They have to take the data and copy it to do the base backup. 8 petabytes, not much fun. At this point, you probably want to investigate using disk snapshots, which means a file system or a device that can handle disk snapshots, rather than doing copy-based. Now, the reality is, at some point, to get it off that device, you have to do a copy. It doesn't completely avoid the copy, but it can. Often, it is a less intrusive path, and you can do deltas that way also. This also requires a certain amount of fiddling up your own backup strategy, which you probably want, a company like us or somebody experienced to help you with. One of the advantages also, especially on network storage, is this can keep the restore time under control because it's often faster you can come up faster restoring a snapshot than doing copying 8 petabytes back out of S3. Now, again, there's no free lunch. Ultimately, those 8 petabytes have to be copied out of S3. When you restore a snapshot on EBS, you get the new EBS volume back very, very fast. What it's not telling you is all the data is still in S3, and it will demand move the data back from S3 as you hit those blocks. So for a while, that database is going to be really, really slow, but you're up, which may be better. You also want a secondary or two for databases this large, and you're already spending $1 gazillion a month on this instance, and now I'm telling you to spend $2 gazillion or $3 gazillion, and I'm sorry for that, but you really don't want to, unless you can be down for a long time. Restores are going to take a long time, so you want a secondary so you can fail over very quickly, and then you can bring up provision a new secondary at your leisure. One thing you can do, and I've seen installations that have great success with this, is if you're running your own running self-hosted Postgres, you're not on RDS or some other database as a service vendor, you can recompile Postgres with a larger block size. It works fine. This reduces the overhead of setting shared buffers large because there are fewer shared buffers in the same amount of space. And 32 kilobytes is an attractive point. That's 4 times the standard 8 kilobytes. One thing you need to be aware of this is there are tools, not in the core Postgres distribution, and most well-written tools don't do this, but there are some tools you might encounter, and statistics queries or monitoring queries that assume an 8 kilobyte block size and don't actually ask the system how big its block size on, and you'll start getting weird results. So, and if you're the author of one of these tools, please query the database and find out how big the block size is. Don't just assume 8 kilobytes. And of course, cache everything. Build roll-up tables for a lot of this data so that you're pre-summarizing a lot of it. If this is time series data, consider something like timescale, which does a lot of the pre-aggregation for you. Cache, have a front-end cache that caches query results, and build application specific caches. Just try and hit the database as little as possible, because huge tables are going to take a long time to query, no matter how carefully you tune Postgres. Okay, now let's talk about systems that are taking under a very high write load. Lots and lots of inserts or something else writing into the database. So the first step is spend all your money on I/O, very fast I/O. If you can get away with it, have local I/O rather than network I/O, network attached storage. Use NVMe local storage. If you have multiple NVMe drives, RAID 0 stripe them. Of course, and make sure you have a good recovery plan, because at this point, if that instance goes down, that database is gone. So you want to make sure you have backups and recovery and recovery situation that'll work. Move PGWall into a separate volume. In most modern systems, this used to be standard advice, but that was kind of back in the spinning disk days where you could have fast disks and slow disks, and that advice is not as popular as it used to be. And for example, if you're on RDS, you don't have that choice. It's all on the same disk, no matter what. But on one of these systems, you might start reaching congestion point on a particular controller, and moving it off into a separate volume can help with that. If you're running your own Linux box, the standard settings on sysctl.conf, that's hard to say, is tongue twister, are not perfect for this kind of thing. We recommend setting the dirty background ratio much lower, to 5%, and the dirty ratio to 90. Quickly summarizing, if the number of dirty pages, that is to say there's changes that haven't been written to disk in the file system cache, is more than dirty background ratio %, so 5% in this case, the system will start writing the data out. If it hits dirty ratio, 90% in this case, it will block writes until it's below 90%. That's bad, especially if you're trying to keep your write rate up. So you want it to start early and not block until it absolutely has to. Setting swappiness to 1 will also significantly reduce the amount of swapping it does, which just reduces I/O. Bandwidth isn't the whole story also. When you talk to a storage vendor, they'll say, our bandwidth is, gazillion bits per second. And you say, that's great. What's the latency? And they'll say, our bandwidth is gazillion bytes per second. They'll kind of not talk about this, is especially true of NAS vendors, because a lot of storage systems that have really high bandwidth have terrible latency, in the sense that how long it takes for the storage to acknowledge an I/O operation. Fast latency is very important, especially on the volume that's handling the write-ahead log, because the write-ahead log needs to be committed, hardened on disk, has to be flushed to disk very frequently, and having a slow latency there will really hurt performance. If you're on RDS and trying to maintain a high load, look at IO2 Block Express. I think you still have to ask Amazon to provision that for your account, and it's quite expensive, but it is faster. It has better latency than traditional EBS. Find a way to get the most performance storage you can. So schema design for very high write rates. Minimize the number of indexes. And especially minimize unique indexes, because unique indexes have locking characteristics, which can be very bad if a lot of processes are all inserting at the same time. Try to use something where the uniqueness is guaranteed externally from having a unique index, like a sequence, something random, although we'll talk about random keys later in this slide. Don't have foreign constraints unless you really need them. Like bad things will happen if you don't have if something fails a foreign key constraint, and there's a likelihood it can. It's better to design your system so that you really don't need to check foreign keys, because you're pretty comfortable that they'll be fulfilled. Don't use highly random primary keys. There's actually an active discussion on the Postgres generalist about this. Don't use out-of-the-box UUIDs, version 4 UUIDs. They have very bad interaction with indexes because it has to bounce all over the index and load a lot of pages to find the right leaf page to insert a UUID. There are UUID implementations, or at least 128-bit random numbers, whether they're technically UUIDs is a matter of debate, that have sequential characteristics at the high bits and random at the low bits, and those work much, much better. 64-bit keys are significantly more performant than 128 bits because of the way Postgres internally represents data. There's kind of a threshold once an object gets bigger than 64 bits on a modern, a 64-bit system. Don't think about having GIN indexes if you have a high write rate. GIN indexes are very slow to update, and while there is an optimization, the GIN pending list, that helps with this, it could also on a high write rate system, it means every time vacuum or something, or every once in a while, the system just grinds to a halt while it posts the GIN pending list, and the GIN pending list implementation doesn't work very well with high insert rate anyway. So don't have GIN indexes if you need to keep your insert rate up very, very high. Avoid large data types. Large being about over 2,000 bytes, where an individual entry is about over 2,000 bytes. Oh, hello, puppy. Because that increases the likelihood you're going to spill things to the toast table, and that will significantly slow down writes, because now it has to do inserts in two different places. Don't have triggers firing on writes. I mean, I think that may seem self-apparent, but I've seen systems where they complain that their write rate isn't very high, and there's a 300-line trigger that gets triggered with every insert. No, that's not helping. Keep the fill factor on 100. Fill factor is a storage setting that you can change for individual tables for how full a page Postgres how full Postgres will allow a page to get on inserts. It's a useful parameter because since when you update a row, Postgres needs to find a place for the new version of the row, and if it finds it in the same page, that's much more optimal. But on a system that is mostly writes and not a lot of updates, setting fill factor to 100 means it will not have to grab more blocks very, very frequently, and that's a significant improvement. So now I want to clarify, this advice is mainly for append-only data sets, ones where you're not doing a lot of updates. So the standard recommendation is you set shared buffers pretty high, 25 to 40%, and you increase checkpoints from the default of 5 minutes to 15 minutes or something or so. This can be suboptimal for a database that is managing a high write rate. You are often better reducing shared buffers to like 10% and leaving it at checkpoint every 5 minutes, sometimes even faster. Excuse me. Because this reduces the amount of shared buffers that it has to flush on a checkpoint. Still keep max wall size fairly high so that when the checkpoint fires, it's because of the timeout. And this has been remarkably effective in some instances to keep the write rate high and not have it grind to a halt when checkpoints happen, because it saturates the I/O subsystem, even with checkpoint completion target at 0.9, which is what we generally recommend setting it to. So experiment with this. Build a staging system. turn your application loose at it at maximum volume and see if this helps. If this is a mixed system, if there's updates and reads, there especially updates, going back to regular checkpointing and the recommendation on shared buffers is a good idea. This is for one that's a very, like, you're absorbing sensor readings from all over the world and things like that. There is a process in Postgres called the background writer that writes out dirty pages between checkpoints. Checkpoints writes them all out. But the background writer is intended to reduce the load and also reduce the possibility that an individual process will discover that there are no free pages for it and it has to write them themselves. The default settings are not very aggressive. You can get a considerable benefit by making them more aggressive, which is what these operations set on. It's also good to turn on wall compression. The amount of CPU it takes is very, very small. And especially if you're checkpointing frequently, you're going to be doing a lot of full page writes. Wall compression compresses full page writes. So on a high write rate system, auto vacuum can have trouble keeping up. You may have to start doing manual vacuums and analyzes, like at the end of each batch or something like that. Also, one thing to be aware of is if you're inserting all of these, the auto vacuum freeze operation may need to be done manually, so that you don't wait until the relatively high settings when auto vacuum freeze will wake up by itself and suddenly start taking a lot of I/O. So sometimes you need to integrate this into a process, like you insert a huge batch and then vacuum or things like that. Also, if you're updating frequently, you are going to get index bloat. And sometimes this index bloat could be bad enough that Postgres will disfavor using the index, and suddenly high-performing queries will just fall apart. So plan to rebuild indexes occasionally and monitor the bloat on them. It's a good idea to increase wall buffers on a high insert rate system, so that it doesn't have to push things out to disk quite so often. 128 megabytes is not a bad place to start, and it's a good idea to turn off synchronous commit. Now, you need to understand what synchronous commit means, which is normally with synchronous commit on, when you issue a commit statement, Postgres will push all the data necessary for that transaction out to disk, and often some other stuff too, and return when it says, okay, if I crash right now, the commit happens, and then if it crashes immediately after the commit, that transaction will be in the database when it comes back up. Synchronous commit off weakens that promise, and Postgres just starts writing the data when commit comes back. It can smooth out throughput considerably on a high write rate system, but it does run the risk that you commit and the system crashes and it comes back up and that transaction is not there. The database won't be corrupted, but it'll be earlier in time than you expected. If the application can recover from that situation, it's a good idea to have it off. You can also turn it on and off on a transaction by transaction basis, if that makes sense. It makes sense in your application. So when you're writing your SQL, use copy instead of insert if you can. Copy is significantly more efficient. If you're inserting one row, it's not, the difference is not huge. But if you're inserting 10,000 rows, doing a single copy instead of 10,000 inserts will be much more performant. If you can't do that, at least use multi-valued insert statements rather than separate insert statements. If you can't do that, use a prepared insert statement. Prepare it first so that Postgres doesn't have to replan it each time. The cost of planning a simple insert is very, very low, but it does add up at high volumes. To the extent possible, combine multiple inserts into a single transaction rather than run each one as its own statement, which means its own transaction. And don't combine a high write workload with a high read workload, because those fight each other for caching space, and you will significantly hurt the write performance, as it has to push things out of the way in order to read data off the disk to get new data. And don't use subtransactions no matter how much anyone begs you to. And don't use them accidentally, because, for example, if you use an exception handler block in a PLBGSQL function, you're using a subtransaction even though you don't realize it. This is a little bit beyond the scope of this particular talk, but there are bad things happen if you use subtransactions too heavily. So replicas. If you have a binary replica that's attached to a high write workload primary, you can have a problem, because on the primary you can have 100 processes all writing to the database, and the poor replica has a single thread to restore that to pick up that information and apply it to its copy. Needless to say, this means you can fall behind pretty fast. There's a tool out there called PG Prefalter. It's a separate process that runs on the replica that looks ahead in the wall to help kind of prefault stuff in so that it's available when the recovery process get to it. That can help quite a bit. Another problem is that you have this replica command archive command that's running every time a wall segment finishes, and there's only one of it, and so it can start falling behind too. PG Backrest, and there are other tools that do this too. I'm most familiar with PG Backrest. Has an option to parallelize archiving, and that can be extremely valuable in these high write load situations. And understand that you probably don't want to directly push things to a very slow storage, like across the public internet to a cloud provider on your archive command. But now I just said don't use read workloads, and I said replicas are problematic. So we're inserting all this data, but how are we ever going to query it? Well, move the read load to a replicas, understanding that this could significant replication lag. If the write load is bursty, if there's this big times that are really high rates and relatively slack times, you can consider using logical replication instead, which has a lot of nice things, because the replica can have a different schema. The logical subscriber can have a different schema from the primary, which isn't true with binary replication. So the subscriber can have indexes and triggers and summary tables that the primary doesn't have, which are all really good things for analyzing this kind of data. The problem is logical replication is not fast. It's even fast. It's slower than binary replication. So if there are no slack periods, if the write rate is continuously high forever, logical replication probably won't be able to keep up. One extreme example is on these continuous high write rate situations is to take a disk snapshot once in a while, remount the disk snapshot, and do your queries on it as an independent system. The data will be somewhat stale, considerably more stale at that point. But the nice part about that is it doesn't interfere particularly with the operation of the primary, and you can still maintain that high write load. One thing that you will often bump into, especially where you have a lot of processes inserting at the same time, is you'll see processes waiting on an extend lock, which is when when a backend has said, I need more space at the end of in the underlying file that represents a table, and the file system is busily tacking stuff on. It doesn't just add one page and then one page and then one page. It has an adaptive algorithm based on kind of how many writes there are onto the system, but it will eventually run out of steam. So you want to pick a file system where extending a file is relatively fast. In our testing, XFS was the faster, followed by ext4, followed by ZFS, and anything NAS-based took significantly more time to extend a file. Okay, so we've talked about lots of data and lots of writes. So let's talk about lots of tables. So, what's a lot of tables? Under 1,000 tables, that's a normal schema, nothing to worry about. Up to 10,000 tables, okay, that's pretty big. Yeah, that's big. Up to 100,000, okay, that's definitely getting big. And over 100,000, wow, okay, you're going to have to take special measures there. Schema-based sharding is the most common reason that this happens, because of you have 100 tables in your schema, you put 250 tenants on a single database, bang, you have 250,000 tables. The good news is it generally works out of the box. PostgreSQL in the past had some issues with large schemas, like in a fairly old now version of Postgres, way out of past DOL, so please don't run it. pgdump, the amount of time pgdump took to start up was based on the number of tables to the 4th power. Needless to say, on a 250,000 table schema, that was not happening. However, pgdump still goes up more or less linearly as the number of tables, And you would say, well, I have a big database. I'd never do a PG dump. But you might without realizing it, because PG upgrade under the hood uses PG dump to move the schema from the old cluster to the new cluster. And can be notable on a very large, this could take a notable amount of time on a very, very large schema. So you're going to need more downtime even for a PG upgrade style upgrade. And if you're on, say, Amazon and you use the console to do a major version upgrade, it does PG upgrade under the hood. So you haven't escaped it there also. So be aware of that. If you can't take the downtime, consider migrating tenant by tenant using logical replication to the new server, and that way you can avoid extended downtime. You just have to cut over one at a time. Also, be careful about monitoring tools. A lot of monitoring tools assume that querying the system catalogs is really, really super fast, so they could do it every minute and there's no problem. This is a little depressing when you come in and see that one of your monitoring queries is creating an 8 gigabyte temporary file on disk to do a sort, which I have seen. So examine the queries your monitoring tool is planning to run and run them yourself on a large schema and see how long they take. And if necessary, either forgo those monitors or reduce the duty cycle on them so they don't run very often. Make sure you increase the number of auto vacuum workers, because again, each auto vacuum worker can only work on one table at a time. You have 250,000 tables. It's going to take a long time for them to grind through them all. So 25 or more is not uncommon. Make sure that auto vacuum work mem is reduced, because each one of those can take up to auto vacuum work mem. And so if it's set to 8 gigabytes, that will cause problems. There's almost never a good reason to set auto vacuum work mem above a gigabyte, but reduce it to a level that you're not going to exhaust memory. Definitely monitor XID age and how long the oldest table it took to get an auto vacuum, because the chance of vacuum falling behind in a very large schema like this, especially if some of the tables are very busy and are kind of consuming all the auto vacuum workers, can be significant. Do as much as you can in these circumstances with prepared statements, because the planner has to query the system catalogs. No surprise there. Normally that's super fast. 250,000 tables, sometimes not so fast, and planning time can start becoming an issue on very, very large schemas. The advantage of a prepared statement is it's planned already. The downside is the plan may not be perfect for the database as it exists now, as opposed to what it was like when the query was first planned. Probably want to bump up max files per process and adjust any system level parameters about the number of open files. Postgres is very intelligent about managing the number of open files, but opening and closing a lot of files all the time is definitely expensive. So you may want to increase that. You may need to increase max locks per transaction, especially if you have partition tables, because Postgres a lot more tables, a lot more locks on tables. And remember that despite the name lock, even querying a single table takes a lock. It's just a very weak lock that doesn't block anything, but it does create an entry in the lock table. And so if everybody's querying every table, you have 250,000 locks, even with just select. And also use a file system that handles a large number of files gracefully. In our testing, ZFS was better than ext4, that was better than XFS, but the difference was not huge. The ZFS to ext4 gap was a little larger. But if you are going to have a lot more files on disk with this. One question is, should I use schemas or should I use databases to do the sharding? Because you can have multiple databases per Postgres instance, of course. There's trade-offs. The good part about using a database is that since most system catalogs are scoped to a particular database, the size of the system catalogs is not going to be as large, and so there's just fewer tables for it to deal with, and that can be a significant benefit. The downside is because you have to specify which database you're connecting to. Well, when you connect to Postgres, it can make pooling much harder because you can't reuse connections all the time. You're constantly switching between databases, so that's a downside. So there are trade-offs here, and it kind of depends on your specific workload. And so we've talked about each scenario, but there's kind of a meta advice, which if nothing else is working or you're starting to run into capacity limits, shard. Because in all three of these scenarios, sharding helps, where you distribute the data across multiple Postgres instances. And it helps with all these scenarios. There's less data per node, so it distributes the right activity, and there are fewer tables per node. So lots of good things. Of course, significantly more application complexity. You can build your own sharding. It sounds intimidating, but often it kind of falls naturally out of your your own sharding model. There's also automatic sharding solutions. Citus is the primary one for Postgres. This is often easier than trying to wring maximum performance out of a single node, especially on a database as a service environment where you can't do a lot of the stuff I've recommended because the instance is just too locked down. Sharding is maybe your salvation here. And thank you. That is the last slide. And are there any questions?
Okay. Let's see. Over in chat, we have PostgreSQL 14 on partitions can get scanned in parallel.
Oh, comment. How did I miss that?
Now you know.
I need to revise that slide.
Yes.
That's embarrassing. Thank you.
It's fix the slide for next time. There's a comment. IO2 block express also has more consistent latency, less random spikes.
Yeah, I mean, IO2 block express is definitely what you want if you're provisioned for it and can afford it. Let's see. I saw a comment about why max cores times 3 because often a lot of the cores are waiting on something. Either IO or a lock or something like that, rather than actually doing work. If your CPU if you're melting your CPU, then yeah, by all means dial it back. But generally, we found time that keeping the parallel workers times 3 was okay for most environments.
Cool.
Yeah, don't do any of these if they're breaking your machine. But in general, we found this is useful.
Yeah. Let's see. The slides when answering Igor's question, the video will be up on YouTube. We'll announce it to the group. We'll also put on our social media, and the slides will be available. So, let's see. Do I see any hands?
There's a question here that's aimed at the audience, but I'll jump in on it, which is I'm curious how many people here run their database at AWS and which disks instances. It's hosted solutions in general are extremely common now. I would say that they are starting to dominate the Postgres world. So with the trade-offs that come from it. So that's excuse me. As far as I would say that most of them are running EBS in general IO rather than using either provisioned IOPS or a fancier IO form. But most of them do not hit these extrema that I'm documenting here, and they work just fine.
Great. Okay, I don't see any raised hands. Oh, no, there's one. Of course, one just popped up. Paul.
Hey, thanks. I'm actually just kind of curious. So I work in the managed database space, and typically we're probably no larger than 9 terabytes. So I'm kind of curious, how often do you see these petabyte scale systems?
Petabyte scale, not very often. But that's a once every 5 years kind of thing. 10 terabyte pretty regularly. 10 plus terabyte a lot. The clients who are starting to get uncomfortably close to limitations in terms of how much storage they can mount, not uncommon. I mean, there's not a mob of them demanding a 128 terabyte limit on EBS or anything, but they do happen. So, I mean, I would say it's roughly an exponential decay curve, in terms of the size of database versus, occasionally a lot of clients will come in and say, we have a really large database. So I say, okay, great. How big? 2.5 gigabytes. It's like, you're okay. It's like, don't panic.
Yeah.
Everything will be fine. I don't, never mock someone's database, but it's like, that's okay. But occasionally they'll come and say, yeah, it's okay. It's a reasonable size. And I was, okay, that's great. How much? 35 terabytes. It's like, you're right. That is reasonable size. You will have some things to think about.
Yeah, I'm happy you covered the pains of backups, because that's always my concern when I start hearing
you have 35 terabytes and you have 35 terabytes here. There's no option other than at some point you need 35 terabytes someplace else, and shoving that down a network cable is painful. The slides the slides will link to the slides from the meeting invitation when they're available, for sure. After I fix my super embarrassing comment about partitions in parallel.
But now you know, so
yeah,
great.
That's, never really know something until you try and teach it.
Mm-hmm. Well, that's also one of the nice things about Pugs is we can all share the information, and so it's like,
this will be permanently recorded a YouTube video that I didn't know that.
It's okay. Let's see. In the chat, minor point: a table can appear to be greater than 32 terabyte because the table itself is limited to 32 terabyte, and its toast table is also limited to 32 terabyte. That said, please partition before you get anywhere near that.
That is exactly correct, because the toast table is a separate table, so it would be interesting to design something that managed to somehow just slide in and write like 63.9 terabytes, where each table, you manage somehow to balance the main table and the toast table to exactly the right point. That would be interesting also from a performance perspective, but I'd love to see something like that.
Great. Okay.
Anything else? Happy to answer.
No more.
Any Postgres questions in general? As long as I'm here, we have 4 minutes. I can. Thank you very much. It was
great. Thank you, Christoph. It's always a pleasure to have you here and your talks. And so let's see, what do we got here to wrap up? First of all, thank you, Christoph. Thank you, everybody, for coming. Lots of thank yous and compliments in the chat, which is always nice to see. Again, thank you to PGUS and PGX for sponsoring our Pug. Let's see, what do we have coming up next? There'll be no March Pug because Scale in Pasadena, California, lands on our Pug date. So let's see, we have events coming up, March 9 to 12, Scale in Pasadena. March 21, we have Nordic PG Day in Stockholm, Sweden. March 22 and 23, PG Day Paris. We will not be doing an April Pug either because PG Day Med, aka PG Day Malta, lands on our date. So we will resume in May. It's just these other conferences are landing on our date, and it's kind of hard to work around being in another country. April 20, we have PG Day Chicago. The CFP is closed. The schedule's up. Tickets are available. For all of the above, all the schedules except Malta are finalized. The Malta CFP is open through Sunday, I believe. And then, of course, in May, PGCon Ottawa returns in person for the first time since the pandemic. Tutorials will be May 30th, talks are May 31st and June 1st. The conference is Friday, June 2nd. Again, we will send a link by the email and also post it on our social media when the video is up on our YouTube. It will also have a link to the slides. For our social media, you can find us on Twitter at Bay Area Postgres. If you're interested in speaking at a Pug, please drop us a note. Talks are generally 30 to 45 minutes. You are welcome to present with a partner. You could do a short talk and somebody else could do a short talk to fill the 45 minutes, whatever works. We are very happy to be a forum for first time or fairly new speakers. If you have a talk you want to practice for an upcoming conference, we're here for you. So drop a note. We'd love to have you. Again, thank you to Christoph for speaking. Thank you to everybody for attending. Thank you to our sponsors. And we'll see you all at a conference in the next couple months, or we'll see you back here in May. Thanks so much. Bye-bye.